Hey there everyone! Today we're running an experiment with Mathworks Simulink to basically aggregate the real-time bandwidth of 4 Nooelec SDRs for real-time spectrum monitoring purposes. Here's how the setup looks like. We have 4 SDRs plugged into a USB 3 hub, and each is connected to one of the 4 inputs of a splitter or combiner, and an ultra-wideband antenna front end to help us survey the spectrum. Now, if you ensure you have a USB 3 hub and connect it to a USB 3 port, you'll be able to power all SDRs simultaneously without issues, since the power is supposed to be sufficient. Now, the Simulink model that you can see here is an expanded version of an example that comes with the so-called software-defined radio using MATLAB, Simulink, and the RTL-SDR ebook. The model includes 4 SDR blocks this time, with a couple of multiplication and division operations here on the left to properly set the center frequency component of each SDR unit here in the middle. Now we have the leftmost section that includes variables such as the global center frequency in megahertz, and tuner gain in dB, and the sampling frequency here. You can change all of these during the real-time monitoring process after you run the model. Now notice that the 4 SDRs are identical in terms of the instantaneous bandwidth each one is providing. Therefore, they would look sort of equispaced when the bandwidth is aggregated, and this is shown in this figure here. This makes the aggregation process a little easier since they share the same sampling frequency variable, which is Fs right here in red. Now the center frequency of each SDR is simply represented by these 4 equations, right here shown below. And they're determined with respect to the global frequency that you want to tune the entire band to. And in this case, it's this black FC in the middle. Now back to the model here, the very last block. Here's a function that plots the spectrum, and it has also been modified to take a variable sampling frequency here, which has been fed into it through a F sampling so-called data store block. This is related to this data store write block, which is ultimately set by this leftmost block sampling frequency here. This has been done to reduce the clutter and the number of connections necessary, since more than one instance exists here of the F sampling variable. Now, if you navigate through the body of this function, the plotting one, you can actually find that the 4 equations that were clarified here at the bottom of this figure are actually reflected, and it's right underneath this data manipulation section here. Now let's try to run the model and see how it turns out. Takes a few seconds to initialize and show the figure. And there we have it. It's centered at around 996 and a half or so. If you want to change that, you can head back to the model itself and double click on the global center frequency block. You got a slider you can fiddle with. Just bring back the spectrum analyzer window to the front, and let's look at the FM here. So let's center it at around 92 megahertz. There you have it. You got the 88.5 and 93.1 megahertz. These are local channels we have here, and you can slide, and that changes in real time and responds accordingly. Now, maybe let's tune to a signal of a wider band, such as an LTE activity, and there is a little around, I guess, 730s, 735 would do. There you have it. It's a little jumpy in nature. And you got some more activity as well in around 875 megahertz. Got some interesting envelopes there. Now you may notice 4 bumps here at the spectrum. It doesn't look like one piece or connected, and this is normal. It's usually decided by the response of the IF filter inside of the SDR's tuner chip. Tuner chips we use here are the popular R860 and R822 from Rafael Micro. And mind you that flatness can improve when you reduce the instantaneous bandwidth you're monitoring in real time, and it starts looking more like one piece the lower you go in bandwidth, or in this case, it would be the sampling frequency here on the left. Remember that you still won't be able to decode information of wideband signals that way because the 4 SDRs are not clock synced in this case. They each have their own TCXO reference. But you will be able to do that though if you can tie all reference inputs to one source of 28.8 megahertz in this case. Now for the global center frequency and the tuner gain variables here on the far left, they can be changed in real time as the simulation is running. So let's try our luck with the tuner gain here since we tried the center frequency before. Bring back the spectrum analyzer window. And let's reduce the gain value down to 20. So we should expect around 20 to 22 dBs of noise floor reduction here. Click OK. There you have it. Pretty much it. The same can't really be done with the sampling frequency here. So for an instance, if you want to change the overall aggregate bandwidth you're monitoring, you'll need to change the sampling frequency, and you can only do that by stopping the simulation first. You head over to sampling frequency box. Let's assume you want to look at only 4 megahertz of overall bandwidth. And in this case, you need to set this to 1 for each SDR. So it'll be a total of 4. Then you'll need to enable the property inspector window, the window here on the right pane, which can be found under the modeling tab. And then in this drop-down menu right here. Under the Properties tab here, the last item callbacks, you'll see the drop-down menu here that has Start FCN star, start function star. This will hold variables that need to be set or initialized right at the start of the simulation or running the model. So this happens to have the frequency of sampling for the RTL-SDR, and you'll need to match this variable with whatever value you have put into this box, the sampling frequency. Set it to 1 in this case, rerun the simulation. You should be able to look at a total aggregate bandwidth of only 4 megahertz. There you have it. This Simulink model is available to you through a link in the description. Have fun fiddling with it, and I will see you in the next one. Thanks for watching.